All right, so today we're going to talk about generative models, and in particular, I'm going to talk a little bit about how we would generate new molecules that we could use in the drug discovery and development process. All right, so how do we generate new diversity? We've looked at a few generative models already. We looked at transformers, and basically anything really with a decoder and a way to sample a latent space is a generative model. We can use this to, we talked about like diffusion models to make images like stable diffusion. We could use generative models to make candidate drug molecules. We could use protein language models to generate entirely new proteins, or use ChatGPT to generate text. I want to talk about one particular class of generative model that has been pretty useful in terms of like generating new candidate drug molecules. And a lot of the exciting work on this has been done right here at MIT by Regina Barsley and Tommy Yakula. So I'll talk quite a bit about their work today. And before we get into kind of the one of the workhorses of generative models, variational autoencoders, I want to step back and just we talked about this a little bit before. I want to refresh our memory as to what an autoencoder is. So an autoencoder is a model where we have some input, we have an encoder, and then we take that high dimensional input, maybe that's an image, right? So if it's 1,000 by 1,000 image, that's 1 million different pixels. Maybe if it's color, we've got 3 million different floating point numbers, like or maybe integers, describing that image, right? And we're going to reduce that into a much lower dimensional space. That's the job of our encoder. And then our decoder is taking something in that space and regenerating the original image. Maybe not exactly, but hopefully something close. All right. So in general, these autoencoders have a bottleneck. They have a latent space that is lower in dimensionality than the input image. And the decoder puts that information back, although it's not always true. Sometimes it can be the reverse. There's a few different types of autoencoders. And just to get some contrast, so a basic, that's essentially what a basic autoencoder does, okay? And the limitation for our purposes of a basic autoencoder is the following. The basic autoencoder, our loss function is really just trying to reproduce that initial image. And so that autoencoder is going to do a few things. It's going to potentially cram a lot of different images together that don't have anything to do with each other. So we don't really have a guarantee that any local point in that latent space that we sample that's near something that we've trained on our training set, we don't really have a guarantee that things in that general vicinity are going to be like similar, if it's an image similar to that image, if it's a molecule similar to that candidate drug. The only thing the autoencoder cares about is compressing all of that information into like a very small latent space and then reproducing it with high fidelity. Okay, so there's no guarantee on the structure of that latent space. We'll also often see convolutional layers involved in the encoder and the decoder, so convolutional autoencoders, and we talked a little bit about this with the UNet that we've seen before. These are also useful for denoising. So we saw these denoising UNet type architectures when we talked about diffusion models, and that was one of the ways that we were removing that noise from the image. Today, we're going to talk mostly about variational autoencoders, and those really solve this problem of figuring out how to generate a latent space that is actually useful, and a latent space where we might have a few examples. So let's say we have a candidate drug molecule that we know has some activity, and now we want to take that into the hit optimization or lead optimization phase, where we're making very small changes to that molecule to improve maybe its ADME characteristics, or maybe improve its binding affinity to its target. We're making little changes here and there. What are the changes we should make? Well, if our latent space is structured in a really straightforward way, then we can go into that latent space. We'll have some vector describing our candidate molecule, and then we'll just add a little bit of noise to it. We'll just like move it like very ever so slightly from the original position, and hopefully it'll give us a molecule that is ever so slightly different than the molecule that we started with. So we'll get into variational autoencoders quite a bit today in terms of how they work in general, and then I'll show you how they've been adapted for chemistry. This is my favorite, sparse autoencoders, which we won't talk about today, but are really becoming popular as a way to take some of these very big, very complicated models and really understand kind of what's going on. So the idea here is if we have a neural net with many different layers, and let's say we have 100 neurons in some layer of a giant model. Maybe it's like an ESM protein language model, or maybe it's ChatGPT or something like that. And we really don't understand what these neurons are doing. Well, we can take those 100 neurons, we can expand them out into an autoencoder that has, let's say, 10,000 different neurons, and then expand it back down to 100. And that's going to separate all of the features. So now it's no longer a sum of like multiple different neurons. We can expand it into a space where each feature of the molecule or feature of the image, or whatever it is, has its own neuron. And it makes it easier for us to really get inside the model and kind of see what it does. It's obviously not efficient. We wouldn't want to do that for inference or something like that. But if we want to understand how these complicated models work, then we can use these sparse autoencoders. Okay, so here's a schematic of an autoencoder. So the idea is we're taking an input, like the picture on the left, and we can sort of splay that out as a big vector, right, which we'll call X here. We use our encoder to compress that into this latent space and then decode it back into the image, hopefully without losing too much of the original detail. So that's a vanilla basic autoencoder. Today, we're going to focus on these variational autoencoders. And here's essentially the difference. We're going to take our image and take that input, and then we're going to encode it not directly into the latent space. We're going to encode it into like you could almost think of it as like a guess of where this input image falls in that latent space. And we're going to have like a mean value, like essentially in the center of where we think the probability of that image is going to lie, and some uncertainty. Okay, so we'll have a mean and a standard deviation, and so they're probably not scalars. Like each of those might be, a few hundred, a vector of maybe 128 or something like that, but probably much lower in dimensionality than the original input, So in this case, that looks like maybe 200 pixels by 200 pixels, so that's, a vector of length 40,000. So maybe we convert that into a vector of length 100, where we've got our guess as to the mean, and then our guess as to the standard deviation. So what do I mean by the standard deviation? I mean that anything within that standard deviation of that mean vector is going to produce an image that is very similar to the input. So I'm going to learn both of those parameters, okay? And you might think, like, why would I do that? Why don't I just, why don't I just guess exactly what the right answer is, because I want to, like, reconstruct my image exactly. And that's the whole point of the variational autoencoder is I'm not just trying to reproduce the original image. If I was trying to do that, I would use an autoencoder. I am trying to structure the latent space so that any points that are within this standard deviation of where I think that image lies are going to produce something similar. So I'm going to maximize the probability of observing my image from anything within that standard deviation, okay? Okay, and I'll get into exactly what the trade-offs are there and how we do that, because there's a few different forces pulling these variational autoencoders in kind of different directions. But for now, all we need to know is my encoder it's producing a guess, and then it's producing some layer of uncertainty on how far can I go in each of the different dimensions of that latent space. How far can I go from the guess and still get a similar image? And we're going to learn all those, right? Those are parameters of our encoder. We're going to learn that. Okay, so I want to introduce some terminology. My encoder is it's basically producing an estimate of given a certain starting image, what is the probability of that image lying in a certain area of my latent space, okay? This quantity is really difficult to compute. So in general, we can't look at an image. So we're making this autoencoder. We can't look at an image and know exactly what is the latent vector that once we put it through our decoder is going to give us the exact image back. We're going to train our network to get pretty good at that, but in general, we don't have a way to solve for that quantity. So that's why I'm referring to it as Q here. It's not an actual probability. It's like, it's our best guess. We're going to train a neural net to try to predict the probability, but it's not, it's not the exact probability. The decoder, if we want to think about it that way, it's taking, it's taking a point in our latent space and it's producing an image, right? Or at least it's producing, some probability distribution that like this pixel has this value and, this pixel has this value and this pixel has this value. So it is producing and we get the image by taking the highest probability value at each pixel or some similar algorithm. But our decoder is basically telling us, if you start at this point in the latent space, here is the probability that, the output is, has this value at this pixel, et cetera, et cetera. Okay. So if we just define P of X given Z as whatever our decoder is doing, and, by virtue of that, we're defining that initial state going into the decoder, like that's our latent state. That's entirely tractable, right? It's just our decoder. So we can sort of know that exactly. So I'm going to call that P. And I'm going to refer to the parameters in my encoder as phi or theta, and I'll refer to the parameters in my decoder as phi. Okay. So our encoder is figuring out like what is the distribution of images or inputs that we put in our latent space, and it is estimating probability of certain latent vector given our image, our decoder. We can define it as computing exactly the probability of a certain image given some coordinate in the latent space. Okay. And at the end of the day, in any autoencoder, at least part of it has to be training the model to maximize the probability of our observed data. Okay, so let's look at the same thing from a probabilistic perspective. Okay, so I'm just going to define a few terms. So we have a joint probability, right? And our joint probability of our image and our latent vector describing the image is equal to the probability of that latent vector given the image times the probability of the image itself. Neither of those quantities we know anything about, but it's also equal to the probability of the image given the latent vector. Well, we know that's whatever comes out of our decoder, and times the probability of that latent vector to begin with. Okay. What do we know about the probability of how points are distributed in our latent space? Well, we don't really know anything about it, but we can also just define it. And so pretty much what people do, which is the same as when this model was first presented, is they say, okay, let's have most of the density at the origin, and then we'll have the probability density fall off as a Gaussian as we get farther and farther from the origin. Okay, so we're going to define the sort of valid distribution of points, or the probability of seeing any particular vector in our latent space. We're just going to define it from the start to be a multi-dimensional Gaussian. Okay, and I'll say that as always, these things are weird in high-dimensional spaces. So I say the maximum probability is at the origin, but because it's such a high-dimensional space, almost all the points are, if you think of if it's 100 dimensions, you can think of like a 99-dimensional hypersphere, and all of the points are kind of at the surface of the hypersphere, because that's how things tend to arrange themselves in high-dimensional spaces. There's just much more volume there, right? Okay, so we can think of this hypersphere in different directions on this hypersphere. That's those are going to be all of the points that we observe, and so you can think of just like pointing in different directions, and each direction you point in, that's going to be like some kind of image, right? And we're not really guaranteed that we're going to sample these images in any sort of uniform way. That space is going to be really strongly defined by whatever we put in our training set, right? So it's going to construct a latent space that is really good at reproducing things in our training set. Okay. So P of Z, we just get to say what it is if we want. P of X, if we can specify P of Z, why can't we specify P of X? Yeah.
Well, because basically our architecture is training the model, to learn P of Z, so we can constrain it to whatever distribution you want. P of X comes from nature, we don't really know what to choose.
Yeah. Yeah, kind of. I mean, it's kind of like saying, okay, if I were to look at all the different points in my latent space, all of the different Z's, and then I were to put them through my decoder and I'd see like what image came out. Like if I only ever train that decoder on images of frogs, and now I put an image of a car in, you know, or like I'm sampling this latent space and I'm like, hey, where are all the cars? There's not going to be a lot of cars in that, you know, I don't know, if the space is infinitely big, like maybe there's some cars there, but like, you know, probably there's not, and we would never find them. And so, because the latent space is kind of being defined by our decoder, we're not guaranteed that all images are there in equal proportions and things like that. It's just going to be like whatever we train this thing on, right? So P of X is like a quantity that's just like so hard to compute. If I have more images of frogs in my training set, then images of frogs are going to have a higher, you know, probability. And in general, like we just don't know what's in that decoder. Okay, so P of Z is something we arbitrarily choose. P of X, you know, that means something about what's coming out of the decoder. So there's no way to predict it. P of X given Z, literally our decoder, we know it. P of Z given X, that's what we're going to approximate. Okay, so I want to start out with, if we just look at Bayes' law and we say, okay, so P of X, so our probability of seeing any image is just P of X given Z, which we know, times P of Z, which we defined, divided by P of Z given X, which, again, we don't know. I'm going to take a log of both sides, okay? And then I'm going to do some rearrangements so that I end up with some terms that you know, are going to be what we end up optimizing in our autoencoder. Okay, so the reason I'm going through all this is like I want you guys to understand all the different forces working in a variational autoencoder, because most of the models we've looked at, they've got one goal, and we just train them for that one goal, and we're optimizing all our parameters for this for kind of this one goal. With the variational autoencoder, there's competing goals, and we need to understand what those are. Okay, so I took a log of a probability, so I'm probably going to get into some information theory and Shannon entropy. And so I'm going to define the entropy, and for folks who took StatMech or thermodynamics with me, this should look really familiar. This is the Boltzmann definition of entropy, but it's just the sum, or it could be an integral in a continuous space of P of X times log P of X, right? And so it's kind of the average value of the log of that quantity. Okay. Okay, and once I've defined that entropy, I'd like to, so that's going to tell me, gosh, if I have a dice that has, you know, like 6 heads, and it's an unbiased, you know, die roll, and then, you know, it's going to be 1/6 times log of 1/6 plus 1/6 times log of 1/6. So it's, you know, add it all together, it's going to be log of 1/6 or negative log of 6, right? That's my entropy in that distribution. If my die is weighted, so it almost always comes up with a 6, then my entropy is essentially going to be 0, Okay, so if I have perfect information on how that die roll is going to come out, then my entropy is 0. If I have no information, then it's like, you know, how many different effective states are there? I take the logarithm of that, and that's my entropy. Okay, so that's we can think of that as computing the entropy kind of compared to like a trivial reference state, where like I'm going to roll the die and you know, I know it's going to come up 6, right? That's our reference state. There's something called the Kullback-Leibler divergence, which is saying, okay, if I want to choose a different reference state and I want to say what's my relative entropy compared to like a different distribution, that's basically what the Kullback-Leibler divergence is computing. So the formula here looks really similar, right? It's, you know, it's got that sum or integral for continuous variables, p of x log p of x, but then it's actually, you know, p of x log p of x over q of x, okay? And the way to think about this is, I always think about it from a biology point of view. I say if there's a natural distribution of things, right? So there is a natural equilibrium between ADP and ATP in the cell, right? ATP, it's got a lot of energy, chemical energy stored in that molecule. And so that energy wants to go downhill. So when the cell is at equilibrium, of course the cell is dead when it's at equilibrium. When the cell is at equilibrium, there's going to be a lot of ADP and almost no ATP, right? It's all going to get cleaved and it's like never coming back, right? That's not really the state that cells live in. So these cells are far from their equilibrium. Well, how far are they from their equilibrium? We could use the Kullback-Leibler divergence. We could say, what's the probability of seeing it in the ADP state? What's the probability of seeing it in the ATP state? And we compare what we expect at equilibrium to what we actually see in the cell, okay? That Kullback-Leibler divergence, if we multiply that by KT, that is how much free energy is available to the cell from ATP, okay? So it requires a certain amount of energy to go from an equilibrium distribution to change all those probabilities into a different distribution, and that amount of free energy is characterized by the Kullback-Leibler divergence. Now, when you see the Kullback-Leibler or KL divergence, it's usually in like an information theory context, so we don't multiply it by RT. But it's really it's kind of the same thing. So we can think about it as like a free energy to change probabilities away from their equilibrium state. Okay. Now, just like if we were talking about a biological system, if we take the KL divergence of P with respect to Q, it is not necessarily the same as the divergence of Q with respect to P, okay? And it doesn't necessarily satisfy the triangle inequality, so it's not really a distance metric. That's why we call it the divergence and not the distance. Okay, so now, now that we've got that terminology, and all I've done so far is give you guys terminology, I want to look at that equation again. Okay, so we had log P of x is are these terms on the right, and this is just Bayes' law, right? The trick that I'm going to do here, and I'm not going to work out the algebra because I probably get it wrong, and you can just, you know, look it up. It's really just algebra. I'm going to take a average over my basically my encoder. So Q of Z given X. Okay. So essentially, what I'm going to do is I'm going to integrate over all Z Q of Z given X for all of these terms, okay? And for the first term on the left, log P of X, if I integrate that with respect to Z and multiply each of those, and multiply the log P of X by Q of Z given X, what do I get? Well, P of X doesn't depend on Z, so like I just get log P of X. It doesn't matter that I've averaged it over, you know, over different values of Q of Z given X, right? And certainly if I integrate over all Z, Q of Z given X, and I integrate over all Z, then I'm just going to end up with 1, right? There has to be some Z, right? The total probability has to be 1. Okay, so my left-hand side doesn't change, but for each of those terms on the right-hand side, if I average them over all values, you know, if I take a weighted average over all values of Q of Z given X, then I'm going to get some different terms. And what's going to pop out is here I'm defining that average as EQ bracket. Okay, so everything in the EQ bracket, it's just you know, it's just integrating over Z and multiplying those terms by Q of Z given X. I'm going to get the I'm going to get that weighted average of log P of X given Z. Remember, that's what we can calculate, right? If we have a latent vector, we can calculate what the probability of a particular X is going to be, minus the KL divergence of Q of Z given X and P of Z. Well, Q of Z given X, that's our encoder. That's how we're taking an input image and we're mapping it to the latent space. So we're mapping it to some distribution in the latent space. And now we're saying, how different is that distribution from the distribution that I said I wanted in the beginning? Remember what I said I wanted? I wanted a multidimensional Gaussian centered on the origin. Okay? So this term is saying, you know, I'm going to look at a bunch of images, I'm going to map them, and if they don't map to something that looks like the multidimensional Gaussian that I said I wanted, then I'm going to, you know, put in like a high value there, right? I'm going to penalize that. And the last term is the KL divergence of Q of Z given X and P of Z given X. Well, P of Z given X is kind of like what we wanted in the first place. We wanted to be able to look at an image and know exactly where it was in the latent space, and I said we couldn't do that, so we invented Q, and we're going to train a neural net to like estimate it, but it's never going to like quite be P. Well, this last term is, how good is our encoder? How far is the guess from our encoder from the actual value of P of Z given X? Okay, so that's a useful term. We can't estimate it directly, but so we've got these two terms. We have these KL divergences. One is the distance of the encoded distribution from our prior, and the other is basically like how much error is there in our encoder. And I guess I didn't say what the first term is. If we average over all values of Q of Z given X, and we take the log log probability of X given Z, well, that's basically our reconstruction error, right? Like when we put things into an autoencoder, and then we look at what comes out, we say, okay, so for this point in the latent space, does it maximize the probability of the data that I wanted to see there? If it does, great. If it doesn't, then you know, we want to get penalized for that. Okay, so now we have so we've kind of rearranged these terms, and we've rearranged them by taking an average over an average over kind of what's coming out of our encoder, and we've rearranged them in a way where we can see relationships between these different quantities, right? We have this KL divergence. Okay, and so if we write this out, then we can take our Bayes law on the top, do this averaging, and then we get three terms. Okay, the first two terms I'm going to call the elbow, the evidence lower bound, and the last term is our encoder error. Right, the last term is divergence between our prediction of what probability of z given x should be and what it actually is. Okay, so we know how to compute both of those terms in the elbow, right? The first term is it's just the probability of our image given z. Our decoder tells us that. The next term is what what's coming out of our encoder, and comparing that to what we said we wanted in a prior distribution. So we know that too. The thing on the left, log p of x, we talked about it. Like we have no idea to predict how likely it is to see a car, especially if we've trained only on frogs or something like that. And the thing on the right, the encoder error, that's like how far is our encoder from like the actual value. Well, if we knew the actual value, like we wouldn't need the encoder. Right? So we don't know what's going on the left-hand side. We don't know what's going on the right-hand side. But we do know that the KL divergence is always a positive number. Okay? And so if we maximize those two terms in the middle, it's going to end up maximizing the probability of x, and it's going to end up minimizing the encoder error, and we don't actually have to know how to compute any of those. Okay, so that's kind of the trick. We're just gonna maximize this thing in the middle because it's gonna kind of do the right thing. Okay. All right, so and then within the elbow, we're going to maximize the elbow, and there's two terms there. One of which we can think of as our reconstruction loss, right? So we've got this point in our latent space. How probable is the data we want to see? That's really straightforward. That's what we would be doing in a regular autoencoder anyway. And now we have this additional loss, which says, hey, I wanted all the points in my latent space to be distributed, as a Gaussian around the origin, right? Okay, so and just for reference, since we know what that prior is, it's a Gaussian around the origin, standard deviation of 1. Then we can pre-compute that a priori. So whatever sigma and mu we end up predicting with our encoder, we can just use this formula, and that's going to be our KL divergence from our prior. So that's fast computation. Okay, so what are the different opposing forces on mu and sigma here? Well, mu probably wants to be in the right spot, and if it was left to its own devices, all the different mu's, the cats would be over here, and the frogs would be over there, and the cars would be over there. They'd probably be really far apart in our space, but we're putting this constraint on. So it's got to kind of arrange them in a certain way, and the same with our sigma. So the broader we make sigma, the better it's going to fit that KL divergence to the prior. The narrower we make it, the less well it's going to fit. Okay, so so we have these opposing forces. Our KL term is going to also pull mu towards the origin. It's gonna pull sigma squared towards 1. But our reconstruction loss is going to pull like separate mu's to separate regions of our latent space, right? Ideally, if we wanted nice, crisp images that really focused on the stuff that was in our training set, sigma squared would get really small, right? And we'd try to like memorize what that training set looked like. But our sigma squared is getting pulled apart, and there's other forces that are preventing it from spending too much time memorizing images. Okay, and this has an effect. So our variational autoencoder, it may end up making images a little more blurry. Okay, and merging similar images together. Okay, but the good side effect of it is that it's really going to add a lot of structure to this latent space. Okay. All right. I'll mention this really briefly because we haven't talked a lot about backpropagation. I think we mentioned it. This is really how it's like the algorithm that is used to update parameters in pretty much all the models that we've talked about, and it essentially involves making a tree of all the computations that we've done so far. And you know, as we go through our model and we make our prediction and we get to the end, and let's say it's a binary prediction of like yes or no, then we're going to output our logits, and we'll take a softmax, and we'll say, oh, you know, it's 99% cat and 1% not cat for this image. And let's say that, in fact, that image is not a cat. Okay, and so now we need to update our parameters because we got that prediction wrong. So we're going to go back to the layer before that, and we're going to say, okay, all the neurons feeding into this, how does like increasing this parameter by a little bit, is that going to raise the probability of cat to be like 99.9, or is it going to lower it to be like, you know, 98? And if it lowers it, then we're going to like tweak that parameter in that direction. And then we're going to step back to the, you know, hidden layer before that, and we're going to say, okay, now all of the neurons that fed into that neuron, well, if I tweak this parameter up, is it going to like move that neuron in the direction it needs to go, or is it going to move it in the opposite direction? And then we're going to like we're going to tweak that parameter accordingly. And then we're going to look at all the neurons in the previous layer and say, well, how did they, you know, all the ones that connected to that, you know, are they moving in the right direction or wrong direction? And that's how we're going to like take our final answer at the end, this probability that comes out, and we're going to back propagate it to every single parameter in the model. Okay. And it's a beautiful and simple algorithm. It just uses kind of the chain rule of derivatives. But we have a problem because everything we've talked about is probabilistic, and I don't think I've told you yet, but when we produced this guess as to what the mean is and then the standard deviation is, the way that we're going to sample it in the model is we're going to like take a point centered around the mean, and we're going to draw it from Gaussian distribution around that point. And the standard deviation of that Gaussian is going to be defined by our sigma parameter, which we're also estimating in the model. Okay? Okay. So now we've got an encoder that outputs a mean and a standard deviation, and then we're going to take a random sample. We're going to take a sample from that distribution. I don't know how to differentiate that. right? It's like a coin flip. Like how do I take a derivative of that? So if I try to back propagate, it's going to back propagate up until that coin flip, and then it's like, what what do I do? Now I can't update the parameters in the encoder, right? And if I get rid of that random sampling, now I'm just stuck with a vanilla autoencoder, and that's not giving me the nice structured latent space that I want. Okay, so the trick is really simple, and this this is used. I think maybe it first appeared in VAEs, and it's used in a lot of different models now that that have the stochastic step. And so what we're going to do is we're going to center on the mean, and then we have that mean plus some normal distribution, which is defined by sigma. And now we're just going to like pick a random number, distributed according to a normal distribution in however many dimensions we have. And we're just going to scale it. We're going to take the mean plus that, that guess scaled by sigma, okay? And so we have a random number coming into our model, but mu and sigma is getting multiplied by that random number, so it's just a scalar. It's just a scalar in our model, and we can back propagate through that, right? Okay. So that's kind of the trick. That's what allows these models to work. And then we can start to explore this latent space. So ideally, if we've done it right, similar examples should be nearby in our latent space, and nearby points should reconstruct to similar examples. Okay, I want to mention this because this is also a really interesting and useful addition to these variational autoencoders. So even though everything that I described to you guys is straight from Bayes' law, so we don't really need to introduce any arbitrary constants there. We could imagine that we've got this elbow term, and we're going to use that as our loss function, and it was going to have our reconstruction loss and our KL divergence of the distribution of our latent vectors compared to our prior, right? And if we set that to 1, that that should be correct, because we sort of derived it from first principles. It technically should be 1. But what we can do, and what ends up being pretty useful, is saying, well, what if it wasn't 1? What if we took our reconstruction loss, and then what if we amped up the KL divergence factor? We made adhering to the prior even more important than we stated initially. Okay, and if we do that, then it costs a lot of. I like to think of it as like free energy. It costs a lot of energy to deviate from that random Gaussian distribution, and the model is going to tend to prioritize ways to separate that data that are actually really useful. Okay, and so it's gonna tend to really hone in on what are the features in the input data that are kind of like most descriptive. And there's lots of cool images you can find on the internet of comparing sort of the latent space of normal VAEs to these beta VAEs where they've kind of amped up the importance of the adherence to the prior. And when you do that and you look at variation across these different dimensions of the latent space, You know, there's cool images of faces where it's, you know, it's just like the same face turning left and right. Whereas, you know, if you do it in a regular autoencoder, like, you know, one person's face just like morphs into like a totally different person's face, and it's not really clear what the meaning of those different directions are, right? So that's been a technique to sort of make it like have even more sensible properties in that latent space. And of course, if we were to take beta and drive it down below 1, then we're going from our variational autoencoder, we're sort of like dialing it down all the way to 0, where it essentially just becomes a regular autoencoder. All right. So that's our VAEs. I wanna talk about another model that it's kind of maybe waning these days, but like who knows? Probably make a comeback at some point, and it's very similar to VAEs. We're not going to go into as much detail, and these are generative adversarial nets, or GANs. And these GANs can produce really high quality images. And the idea behind the GAN is we've got 2 models. One is a generator, and it's generating, you know, some sample. Then we have real, let's say, images, and we're going to sample those. And then we have another model, which is a discriminator. And the discriminator's job is to figure out, okay, is the image or, you know, molecule or whatever you're feeding me, is it from the training set, or is it from the generator? And so the generator is under pressure to try to make fakes that look like they could have actually come from the training set. And the discriminator is under pressure and is being optimized to be a good classifier and be able to spot the fakes from the real ones. And so if we can train these at the same time, then they're, you know, in the best of all worlds, they're going to be improving together. And it's going to end up with being able to produce examples that are very difficult to distinguish from kind of like what's in the training set. That's a little different than the VAEs, because with the VAEs, you could see with the image that I put in the beginning, the one that came out was like a little more blurry, you know. With GANs, because they're being trained to, you know, fool a classifier, they're going to look really crisp and look like real images. The advantage of the VAE is it's a little better at getting a wide diversity of images, molecules, whatever. Whereas the GANs, because they're so hyper focused on making things that look real, it's often the trade-off is well, they're not, you know, they don't make that many things, right? So if it's faces, maybe, you know, maybe there's only like 12 faces essentially that they make, but they make them really, really good. Whereas the VAEs can make all kinds of faces, but some of them are sort of like blurred, you know, morphed images between two. Okay. And the, you know, the thing, the generative model that both of these are kind of being replaced with quite a bit, of course, the diffusion models, which we talked about earlier. We're not going to go into those this term. We're not going to go into them in more detail, but the math that we've just gone through for the VAEs is sort of the starting point for understanding the math behind diffusion models. So I encourage you guys to look that up. Okay, so for the remainder of today, I want to talk about some of the cool work being done right here in this building by folks at MIT. And the first one is a variational autoencoder for generating molecules. And so last day we talked about different ways to represent molecules. So one of them was smile strings. We've also talked about lots of models that can act on sequence data, right? And then produce like new sequences and things like that. So a lot of the work that had been done up to this point was taking those smile strings and, you know, maybe putting them in a transformer or, you know, an RNN or, you know, maybe some sort of VAE, and then trying to produce new strings that were similar, right? This is it's a pretty obvious idea. When I taught a similar class, it was kind of the, you know, first time I've taught a class like this in the spring, I said, oh, this would be a good like homework problem. I'll like give the students like 2 million smile strings, get them to make a transformer that will like learn from those and be able to produce new smile strings. It was an absolute disaster. It just like, it absolutely did not work because it produces things that, you know, if you look at those smile strings there, like, yeah, you can train a model to produce strings that look like that, but they almost none of them correspond to actual molecules. So that's one of the problems. And the other problem is, you know, if you think about everything we just talked about in terms of our variational autoencoder, it had properties that were really nice. We want to be able to, like, you know, take a lead compound, map it into our latent space, and then start to sample points around that and get slight modifications of our lead compound, right? Well, if we look at those two chemicals right there, can you spot the difference? It's just one methyl group, and it's, you know, it's either on the you know, one member of that ring highlighted in red, or it's on the other one. So it's like a very small change. And now if we look at the smile strings that represent those two compounds, they're like completely different, right? So those are the canonical smile strings that we talked about, where smile strings are not unique, but you can choose the canonical one. So even if we choose the canonical one, they're totally different. And so trying to train a model like a transformer to operate on these strings, it's operating in a space that is like just really, really different from the space where intuitively we would want them to be operating. So these guys came up with a different way of representing them using molecular graphs. And the basic idea, this is the basic idea is, you know, using the molecular graphs, and you know, I think one of the other things that have been tried up to this point is taking those graphs and building them one by one in terms of atoms. Now, the problem with building them atom by atom is, if we want to get from, let's say, the starting point on the left to the ending point on the right, and we're adding one atom at a time, well, the starting point on the left, that's a valid molecule, but all three steps in the middle, they're not valid molecules. And so ideally, we would want our model to constantly be thinking about and be constrained to valid molecules if we want like a valid output. So their idea was not atom by atom, but let's cluster these molecules into different nodes, into different groups of atoms, and then try to build them that way. And so that's basically what they do. And so their model is called a junction tree VAE, and essentially what we've talked about is taking an image or taking some sort of input and mapping it into like one particular latent space. what they do is they take their input, and if you go down the left-hand side, you see how they take that input, turn it into a graph, and then they embed that graph in its latent space, okay? And so they'll have in their autoencoder, variational autoencoder part, they'll have a mu for that graph and a sigma for that graph. But then they also decompose it into a tree. And the tree is essentially what are the different parts of the atom. And they basically they use an algorithm called a junction tree algorithm, which is used in kind of analyzing like graphical models, and they've adapted it to these molecular graphs. And so the junction tree model essentially tells you like where to cut these things, how to cut them into smaller pieces, and then join them in a tree. So they're converting into a graph and then also a tree. And so they have two latent vectors, and they just concatenate them, right? And so they'll have two concatenated vectors for the mean, and then two for the standard deviation, and then they can feed that into a variational autoencoder. I'll skip through how they build it back, but it's really a cool paper, so I encourage you guys to check it out. And we'll jump to kind of some of the results, and this is exactly what we wanted to see, right? So on the left, here's a bunch of molecules that are sampled from the prior distribution. So just going to that latent space, going to that multidimensional Gaussian, and just pulling random points out. These are the molecules that come out. And then if we go kind of towards the center of that space, and we pull out like lots of molecules that are really close to each other, then you see that field on the right, and you see a lot of molecules that are like very similar to each other. And you can see the ones in red and the ones in blue. They're actually made of the same parts and even the same tree of how they go together, but they're put together in like slightly different ways. Okay, so you're really exploring like a lot of the variation there. Okay. These guys also, they've done a lot of work with these molecular graph representations. And so this is another paper that they did in collaboration with Jim Collins, who's over in the IMES department here at MIT. And this is using some of those models to improve antibiotic discovery. And so traditionally, we would start on the right, and we'd do small molecule screening, right? And then we'd get our hits, like we talked about the other day, and we try to validate those, and then put those into our lead pipeline, and optimize those. That's pretty expensive, especially if we want to screen lots of molecules, and it's hard to get libraries that are that really hit all the chemical diversity that's out there. So what they've done is they've built a graphical neural net like we talked about the other day, and they've got their own message passing strategy, and they're using that to make predictions about some property of these molecules. And the specific property that they trained it on was being able to predict to what extent they will impact the growth, I think, of an E. coli data set. Okay, so how does that graphical model work, or that molecular graph? Essentially very similar to what we looked at the other day when we talked about graph neural nets. But the real innovation here was rather than treating rather than having a latent vector on each of the nodes, they have a latent vector on each of the bonds. And so here you can think of the atoms as connecting different bonds together. And so the bonds then are passing messages back and forth according to some message passing rule. And this ends up being, graphical convolutional neural net that performed pretty well. And so the first thing they did is they went to the Broad Institute, where they had 10,000 different chemicals in a library, and I think most of these were either FDA approved or they had been, they had made it to some stage in a clinical trial in the past. And so they have this drug repurposing library. And essentially what they did is they took all the molecules and then looked at how they inhibited the growth of E. coli. And you can see over there in panel A, the blue ones don't inhibit E. coli because they drew the threshold that, it has to grow at least 5 times slower. And the red ones on the bottom, those did inhibit E. coli. And so they were able to predict, if we look at the ROC curve, where we plot our true positives versus false positives, the area under the curve is almost 0.9, which is pretty good. Okay, and you can go through the paper in more detail, but if you want to check out panel D, they've taken the 100 top predictions that that they thought, these are predictions that were in their test set but not in their training set. So they've taken their top 100 predictions, and you can see like almost half of them inhibit the growth of E. coli. Whereas if you look at the bottom predictions in panel F, like very few of them inhibit the growth of E. coli. So the model has a lot of predictive capabilities, even in the top 100. It's only getting 50% of them right. But remember, like our standard approach to drug screening and drug discovery is just looking at hundreds of thousands or even millions of compounds in hopes of like finding one, right? In hopes of finding like at least a small number of leads. Okay, so they took, I think, their top-ranked molecule from this repurposing library, and it was some kind of kinase inhibitor, of a human kinase. And then in the bottom panel on the right, you can see how, as they titrate the concentration of that molecule up, they see declining growth of E. coli. They also looked at the same drug with Acinetobacter, which is one of the antibiotic-resistant organisms that's quite concerning, and was able to, this molecule they've named as halicin was able to inhibit the growth not only of E. coli but also the Acinetobacter, and they also tried it on C. difficile. C. difficile is the most common gut infection, that hospital-acquired gut infection. And they were able to show that also in a mouse model. So, by building a graphical model, this time with the bonds rather than the atoms, and putting that through a message passing network, I think with like 3 convolutional layers, they were able to predict its effect on, if its efficacy as an antibiotic. And they were also able to identify some compounds that were in a much larger database that also might have antibiotic effects. So there's a lot of work going on. It's pretty early stages, but still exciting times on trying to use some of these tools to speed up the drug discovery process. And this is from a paper in Nature a few years ago, looking at like what kind of the progress that AI-enabled drug discovery is making. So on the left, you see, I think mostly like startup companies that are doing AI-enabled drug discovery. And then for comparison on the right, you can see like how many different research programs, how many different essentially like drugs in the pipeline at the top 20 pharma companies. And you can see the rise of these AI-based startup companies is it's happening. They're catching up. So that's really exciting. Okay, that's it for today. And Thursday, we'll kind of I think we've covered a lot of the material that I wanted to cover for this particular section. So on Thursday, I'm going to walk you guys through some real practical examples of how to do this. Will probably be informative as you think about how to tackle the P set. And then I'll talk a little bit about just in general what are some of the tools and tricks to train these models. So see you then.